It's a pleasure to be here and talk about something I really care about. I started this journey around 2000, 1999, as an interested citizen and skeptical of climate change. But I said, well, you know. So I started reading about it. And after a couple of years, I said, you know, there might be something there. I'm not really sold on it. And after a while, I said, no, there really might be something there. And that's the beginning of the end. So I was a very happy researcher at Stanford, and people at Berkeley Lab, they wanted me to be director of Berkeley. I said no twice. No, I'm not interested. And let me tell you, you have to say no 3 times. It's in the Bible. And finally, the then director said, look, you know, if there's a 5% chance you're going to take the job, come. And otherwise, don't waste our time. You don't want to waste your time. So I thought, I'm here going around giving talks on climate change. And Berkeley Lab, those of you who don't know, it's just adjacent to the University of California, Berkeley, not to be confused with Lawrence Livermore Lab. And when I was a student at Berkeley, I was also an employee of Berkeley Lab as a graduate student and a postdoc. And it's a very distinguished laboratory. 15 people who worked there got Nobel Prizes. But that's the least impressive. The most impressive, about 36 young scientists who were trained there went on to get Nobel Prizes. Okay? Harvard has a similar record, University of Chicago, not Berkeley, not many other places. So I said, if I could join that lab and get people interested in the science and engineering that could help with climate change and technical solutions, not political solutions, it would be worth it. So, as I said, that's the beginning of the end. So now I'm going to talk about something I care about. I was going to step down after that and you don't want to hear this. So anyway, I'm not a politician. I didn't know President Obama. I never campaigned for anyone in my life. And in the third week in November, I get this strange phone call. President-elect would like to talk to you about an important job. I'm not sure I want to talk. I'm not looking for a government job. How important? Secretary of Energy. Okay. That rises the threshold. So I met with him. I'm 20 minutes into my talk, and meet him in the 15th floor of a Chicago building. It's warm. It's okay, he's from Hawaii, so I take off my jacket, I take off my tie. He comes up to me and says, everybody's telling you you should be the new Secretary of Energy. And I say, who are these future former friends of mine? He doesn't like some of my jokes, he likes some the other. Anyway, so after an hour just one-on-one, I call my wife and say, if this man asks me to be Secretary of Energy, I will say yes. I was that impressed with this guy. And he asked me a week later, week and a half, and I said yes. And again, that's my ruling. Okay, so let me talk about why I was motivated to do this. I'm going to talk about climate change. This is data you might know of, but we're going to talk about carbon dioxide. I'm just going to start the clock at, some arbitrary date. We'll call it 1 AD, and go forward 2,000 years, and that's the carbon dioxide level, and this little arrow is where we are now. And you could say, is this a coincidence? Is this something that, carbon dioxide has gone up and down over 1 million years, actually hundreds of million years, and it's very correlated with temperature. So what's different about this time? Why isn't it the same? And I have to say that there is a smoking gun. Because if you look at the carbon dioxide levels of carbon-14, which is made in the upper atmosphere with cosmic rays, and it goes down to the biosphere. Carbon-14 is in all of us, and it's radioactive dating. And when you die, and it's been rumored we'll have that. Imagine you go in a coffin, and you're very isolated from the rest of the biosphere. The carbon-14 in your body will decay with a half-life of 5,700 years. So after tens of thousands or a million years, you have no more carbon-14 in you. It's all decayed to nitrogen. They exhume you and all your friends, me included. And they put us in a fossil fuel plant and they burn you for electricity. We have no more carbon-14. And if that is a lot of carbon, the ratio of carbon-14 to carbon-12 gets diluted. It quantitatively agrees with the amount of fossil fuel we put in. Now think about that. If your natural cycles of trees and oceans, most of the cycling times of that are less than the carbon-14 lifetime. So you reach steady state. So it had to be sequestered for tens of thousands of years, maybe a million years, okay? Fossil fuel does that. Trees don't do that. A lot of the ocean doesn't do that. So I consider this the smoking gun, that this time it's different. It's not biosphere circulation. All right. You can ask other questions. So the glaciers melting, is the sea level rising? The short answer is yes, but I'm going to give you a history lesson, not a climate prediction. So let's go back. On the right-hand side is time 0, where we are today, and you go backward, and you see the temperature on the right-hand side in black going up and down like a yo-yo. That's natural causes, because I can assure you 50,000 years ago, humans had nothing to do with this. You look back in the last warm period where that red arrow is, and we're about 1.5 degrees, maybe 2 degrees. That warm period was warmer by at most 2 degrees. What was the sea level during that time? How do we know what the sea level was? Well, you can look at fossils of seashell critters who live at the border of land and ocean. You can radioactively date them. Where were they living? You can't look at it in one place. You'll have to look in hundreds of places, because land goes up and down. And so what we find is that in this warm period, roughly 125,000 years ago, the sea level was 6 to 9 meters higher. So that's history, not a climate model. The other scary thing is that if you look at where we are in carbon dioxide levels today versus the prehistoric record, geological record, we have to go back 3-4 million years ago. And at that point, we're 3 degrees warmer. Okay, so this is why there's some concern. And in the sea level rise, 20 years ago, 10 years ago, we thought it would take thousands of years for the glaciers to melt. And then with satellite measurements of Antarctica and Greenland, all bets are off, because now the estimates are being rushed forward. Maybe half to 3/4 of that 6 meters higher will occur in a couple hundred years. Not to worry, if you have beachfront property, that's not to worry. But 10% of the world's population lives within 6 meters of sea level. All right. There's other things that people have noticed. There's increased droughts. Water aquifers are depleted in many parts of the world, including the United States, especially in the Midwest and California. Forest fires, all this stuff. And so these are the water stress areas in the world, and the United States lights up. All right, so if there's water stress and a failure of agriculture, borderline countries fail. And when borderline countries fail, they get desperate. As we've seen, maybe 5 million refugees in Europe over the last 3 years, and then Europe is undergoing a crisis. We've seen, having nothing to do, not very much to do with climate change for sure, in Central America, wanting to come to the United States because they're desperate. But in this scenario where agricultures fail and economies fail, we're not talking about 5 million, we're talking many, many more than that. When I was Secretary of Energy, I was talking to some Indian ministers who, it wasn't a debate whether climate change was happening, but they were worried about Bangladesh because it's 140 million people, very low-lying thing. They could either go to the mountains, but there was nothing, there's only poverty there. So the Indian ministers felt they would go over the border. Largely Hindu country, largely Muslim country, very, very poor, and they were desperate. What are we going to do? Do we shoot them at the border? We can't do that. Okay? So even in 2009 to 2013, there was this concern about what would happen to political stability. All right? So this red line is the line that we need to keep below 1.5, 2 degrees. And this is, the black line is where we are in cumulative carbon emissions. Why cumulative? If you stop dumping sulfur dioxide and nitrogen oxide into the atmosphere, the lakes will clean up. The acid rain goes away in 20 years. What about the carbon dioxide? Well, half of it gets absorbed very, very quickly by land, more plant growth, the oceans, and the other half kind of circulates back and forth, and we don't know exactly how long it is, but the best scientific estimate is 10,000 years. So we're not worried about 2100, we're worried about 100 AD, which is a different dimension. For that reason, we think of cumulative emissions. It doesn't go away for roughly half-life 10,000 years. All right. Let me also remind you that 3/4 of the carbon emissions occurred since 1950. And although Yogi Berra did not say that, he could have said this: if you don't change direction, you will end up where you're heading. And so in the next 35 years, 30 years, based on current emissions, we pass through this dotted line. Okay? So it's not if, it's when. And then how much past the dotted line, we don't know. So that's not good. That's the bad news. So let me tell you a little good news. It's kind of like this joke. It's probably in politics, but I'll say it anyway. O.J. Simpson's on trial. His lawyer goes up to O.J. and says, "We got the DNA tests. It's not good news. There's good news and bad news." So O.J. says, the lawyer says, "What do you want to hear first? Tell me the bad news." "Your blood tests are in, your DNA is everywhere." "Oh, that's bad. What's the good news? You have low cholesterol." So anyway, here's the good news. We can do something about it, and there's technologies that can do something about it. So if you look at this graph from IPCC, the orange at the bottom, or whatever it is, yellow, I don't know what it is CO2 emissions. But I want you to pay particular attention to CO2 from forestry, agriculture, methane, of which more than half is due to garbage dumps and agriculture, and N2O, which is due almost exclusively to fertilizer runoff. So if you look at that, there's more greenhouse gas emissions from agriculture and land use and forestry than there is from electricity generation in the world. So I wanted to draw your attention to this. And we've actually geoengineered the world in ways that it's hard to believe. Half of the habitable land in the world is used for agriculture and grazing, okay? And so let me give you examples of geoengineering. it's a quiz. I'm a professor. And the quiz is, can you pick out the native corn from the corn we eat? That's the wild corn. It's unrecognizable from the stuff we eat. Let's go to animals. Beef cattle, pigs, broiler chickens. The full circle is the natural lifetime of these animals, and the little red thing is the time when they're slaughtered. Broiler chickens, it's 40 days from hatching when they're slaughtered. Beef cattle, it's only 1.5 to 2 years before they're slaughtered. Pigs, roughly 24 weeks. And by the time they're 24 weeks, they're 280 pounds. Okay? So this livestock has been bred to grow very, very efficiently, very rapidly, in a small fraction of their natural cycle. Not only that, if you think about all the animals we breed and eat, and us, and you ask the question, think of all the mammal biomass of the world, humans and the animals we eat, and the rest of it, the mice, the rats, the lions and tigers and bears and deer, whatever. What's the fraction of humans and animals we eat to the rest? We're 96% of mammal biomass. Okay? We've reshaped the world completely. In the amount of land we've put under agricultural production, half of it, and the whole mammal world. All right. These aren't mammals. I guess they're mammals. Turkey's close enough. Slaughtered, the Safeway turkey 3.5 months after they're born. But they're not like the usual birds. They're so breast heavy and they grow so rapidly, they're not going to really reach adulthood. They'll fall over. But that, no matter, they're slaughtered very quickly, and they can't mate, so they're artificially inseminated. Now, if you wait for Big Tom at 24 pounds, they're more like real birds. But let me remind you what real turkeys, wild turkeys, look like. These are wild turkeys. Now, we don't know how old they are. We know how old this wild turkey is. Wild Turkey 101, 8 years, or so they claim. Okay, let's move on. Let's talk about the carbon emissions. China is now the leader in world carbon emissions. It's double the United States today. The United States comes in, and the whole EU 28 or EU 27 plus 1 are less than that. But if cattle we eat and the dairy cows we raise were a country, they would be more carbon emissions, greenhouse gas emissions, than the entire EU 28. Okay? Kind of profound. Now, I'm not here to tell you you shouldn't eat beef. That's a personal choice. However, you probably have people at home, like your kids or your grandkids, who are beginning to realize that if they can do something in the world as a personal choice, don't drive a big car, don't even own a car, and meat substitutes. And so these are two meat substitutes: Impossible Food burgers and Beyond Beef. There are many more. Sadly, Impossible Food burgers are impossible to buy in a supermarket. Hopefully that will change. And there's really interesting chemistry associated with Impossible Food burgers. I happen to know because I know the founder of this company. He was a very distinguished biochemist at Stanford. And he calls me up and says, "Steve, you inspired me. I quit my job." He was a Howard Hughes senior medical advisor. I said, "You did what?" He said, "If you are willing to become Secretary of Energy, I need to do something about climate change, but I'm just a chemist. So I'm going to make a vegetable product that could be substituted for beef." And so in the flavorings of the chemistry for beef, he found that the blood taste actually comes from the molecule for blood, hemoglobin. So he looked at various varieties of hemoglobin and found remarkably that hemoglobin from soy is pretty good. But he couldn't get enough hemoglobin from the soy roots, so he finally gave up the ghost and said, we're going to genetically engineer yeast to grow hemoglobin, fake hemoglobin, to give you the blood taste. And then they did a little taste testing with soy hemoglobin, this hemoglobin, that hemoglobin, and found that the people actually liked the vegetable form of hemoglobin better than the beef form. I did not ask him if he did taste testing with human hemoglobin. Don't want to go there. But anyway, it's not bad. They're still working out. It's improving. Let's talk about fish. This, on the left-hand side, is global wild salmon catches, and it's going down, down, down. And most of the fish the humans eat today around the world are farmed. They're not wild caught. You can tell because if you go to Safeway or Whole Foods or wherever you shop, the wild catch salmon is like 3 times more expensive than the Costco salmon. It actually tastes better too, but never mind that. So then the question is, can you feed a growing population? And this is maybe creepy for some people, but it's okay for me. They put 2 genes in salmon that were salmon genes. One gene was from Pacific Chinook salmon, and another from ocean pouts, not exactly a salmon. So these are 2 salmon. One of them is the kind of wildish sort of, or farm salmon. The other bigger fish, like 3 or 4 times bigger, is this other salmon. Now, it took 19, maybe 20 years to get FDA approval. And the deal was, there's no way these salmons get exposed to a lake, a river, or the ocean. They're on land, heavily filtered water, and that's it. And yet, this company feels, Aqua Advantage, thinks that even despite that, it's a way of getting more meat on the table for the same amount of feed. Now, for America, we can afford Atlantic cod or whatever. But for a growing world population, this is an issue. Let me also tell you about some exciting things. There's a company in the Bay Area that called Pivot Bio, and they've figured out how to get microbes that they put onto the seeds of corn, and the microbes enter into a symbiotic relationship with the corn so that it was imitating legumes, which actually fix nitrogen. And so all of a sudden, the corn is making its own fertilizer with the microbes. And with fertilizers like 2% of energy in the world. And when farmers over-fertilize, the fertilizer runs off and makes the N2O. So agriculture, because of the energy cost of fertilizer plus the nitrous oxide, is a big greenhouse gas emissions. So if you can get plants that self-fertilize, it's a very big deal. So this is now out there commercially. The company is trying to get farmers who really believe in this, and so we're in the 2nd year of not testing, but commercial production. So that's also kind of cool. Now I want to switch gears, and as a quote when I was Secretary of Energy even before, that I'm quite fond of, it was said by the former Saudi oil minister, Sheikh Yamani, and he said, the Stone Age came to an end, not for lack of stones, and the oil age will end not for the lack of oil. That's not why he's the former Saudi minister. What he really meant is that you went from stones to other things because the technology got better. And as long as oil is a good technology, it will stay there until you invent something more. So you transition to better solutions. And if you don't find a better technical, including economic solution. And if you're a country that has trillions of dollars of money under the ground, it comes out. Okay? Let me tell you how good petroleum is. If you think of energy, on the x-axis is energy per unit weight, on the y-axis, energy per unit volume. You want energy that's compact in volume and compact in weight, and leading the charge are diesel, kerosene, and gasoline. Kerosene, jet fuel is mostly kerosene, and a few additives, so if the jet engine goes out at high altitude, you can restart it. Very important. Okay. The other thing is fat, body fat. Same high energy density, because nature figured out if you want a mobile platform, you want the highest energy density possible, which is oil-like compounds. Down here are batteries, like really close to zero, okay? But it doesn't have to be that good, because batteries actually are much more efficient. They're 95% efficient. The internal combustion engine car is only 30% efficient. So they actually come and meet not so far away. Another quiz. What does a Boeing 777 have in common with bar-tailed godwit? You probably don't know what the bar-tailed godwit is. It's a little bird about this big. And the answer is, this is 4 years old. Both can fly nonstop 11,000 kilometers. The really long-range 777s are now 1,400 kilometers. So they've outpaced the bar-tailed godwit. At takeoff, both the plane and the bird are more than 50% weight in fuel. This bird lives half the time in Alaska and half the time in New Zealand. Okay? And most of them kind of stop off in China for refueling, but then they started having really light GPS sensors on them, and they found out some reasonable fraction of them actually take off in Alaska. They fly on the Pacific, they kind of look down, they see Hawaii, and then they turn right. They don't land. And they land one skinny bird. Okay? It's amazing. I don't know how they sleep, but never mind that, because it takes a couple of weeks. Okay. So that's just to impress upon you how good liquid hydrocarbons are. Now, in the meantime, solar and wind are really getting terrific. Solar, for example, in the Middle East, power purchase agreements. That means you get an unsubsidized bid, lots of sun, including profit, and contracts are now selling for 2 cents a kilowatt hour. And the oil and gas companies around the world and multinationals think in 10, maybe 15 or 20 years, renewable energy will be 1.5 cents a kilowatt hour, which is really cheap. However, it's not on all the time, but because of that, in addition to the solar and wind, you have to have backup power, you have to have energy storage, you have to have enhanced transmission and distribution systems. Let me also say that I think we're going to have these things. It's going to take very inventive people, but I'm very optimistic. But let me talk a little bit about just transportation electric vehicles. An optimistic view is that by 2040, maybe 55% of all personal vehicles and light-duty pickup trucks will be electric vehicles. So, why such a fast transition? Let me go back in history. This is a picture Easter morning, 1900 New York. It's the Easter parade. And here's a picture Easter morning, 1913, Easter parade. What's the difference? One car, one horse and buggy. 13 years. What propelled that in 13 years? Well, because you need a huge infrastructure change. You need better roads, you need a gasoline supply chain, you need repair shops. And what propelled it was a serious environmental problem. What's the problem? The problem was in 1880, 160,000 horses in New York City, producing 3 to 4 million pounds of horse poop a day. It's piling up everywhere. Along comes a poopless carriage. Perfect. Okay? So it was the poopless carriage that actually made the adoption of automobiles really fast. Let's fast forward 100 years. This is Beijing in a bad air day. And we're beginning to find out that PM 2.5 is particularly dangerous. And large epidemiology studies being followed up by even larger studies, all confirming that even a small amount of PM 2.5, in this case, in this study, only 5 micrograms per cubic meter, give you an 18% higher chance of getting lung cancer. The average air in Beijing in 2013 was 76 micrograms per cubic meter. So this is pretty serious stuff. Delhi is much worse. Delhi is like 300 or 400 average. And so in 2016, Beijing was like a pack of cigarettes a day. So Delhi, you're 3 or 4 packs of cigarette a day. Everybody smokes from day 0. Here's the scary thing. Lung cancer is not the biggest problem. Just like cigarette smoking, it's coronary disease, stroke, lung cancer. So let's talk about the batteries. Will there be enough natural resources to supply the batteries? The batteries that we use today in our cell phones and our vehicles use a lot of cobalt. And so this is a projection to 2030 only, where you see the EV batteries, the portable batteries, and non-industrial batteries, and you see that there's going to be a rapid demand, and the black line is the supply. And so if EVs get really popular, they're going to get very expensive because the world is not going to have cobalt. And so the word is you've got to get rid of the cobalt. In fact, even nickel will be too expensive. The good news is the cost of EV batteries has declined tenfold in the last 10 years. It's going to decline another 2 or 3-fold. And the energy density is going to go up to here. Why am I so confident of that? Because I'm on the board of a battery company, and we're now shipping samples to companies with that energy density. So it's not a laboratory thing, it's a production thing. And so that's very good. And so the energy density will double. The price, I think, will go down at least another 2-fold. All good news. Let's talk about the natural resources. Right now, today's batteries, let's say the Tesla, the materials are about 30% of the cost of manufacturing. Will we run out of lithium and will we run out of cobalt? The answer to cobalt is yes. And so in order to get the price down, continue to drop down, you need to think about lithium supplies. This is a projection to 2030 and what's going to go on. So it's personal research that I've publishing. We've just submitted the paper with Chung Lu, who's now an assistant professor at the University of Chicago, with Yi Shui, who's a professor at Stanford with me. And so we've just submitted this paper where we're showing that you can extract lithium from seawater, hopefully economically. The cost of electricity is about 50 cents, the cost of lit per kilogram. The cost of lithium is about $10 to $15. And seawater, there's 5,000 times more lithium than in brines and ores. So this is good. So maybe this is under control, and we're working on making sure that this process cannot be poisoned and can go many, many cycles. All right? What about the cobalt? Cobalt, anticipating success 20 years from today, you can't use cobalt or nickel. And so the important target or wish list is you have lithium, which I think is solved, with sulfur. And there are eyeballs with sulfur, because you got to get the sulfur out of fuels for low sulfur fuels. So piles and pounds of sulfur are building up all over the world. I advise Royal Dutch Shell, and they're trying to get rid of their sulfur. They stick 40% of their tar they make for roads are sulfur, because it's filler and it's free. Okay? So if you can make a battery of lithium metal and sulfur, you're good. But the trouble is, in the sulfur lithium, if you want to charge the battery, which means you got to get lithium back to the anode positive side, some of the sulfur comes along with it, and it poisons the battery, and it gobbles up the lithium. And so the issue then becomes very clear. If you want sulfur for scale, you got to get a better separator that separates the sulfur from the lithium as it comes over. And so we're working on it. I'm very, very optimistic. And this is a separator. I'm not going to show you the real data of the batteries, but we've got 1,000 cycles of lithium sulfur metal, but it decreases its capacity by about 50%. We got to get it to only 20%. And if we can do that, this has hope, okay? The batteries get cheaper and cheaper. Electrochemistry, I'm not going to go into this. This is electricity to make chemicals. And I know you're not mostly a technical audience, but so here's the deal. You're mostly engineers, right? Anyone an engineer here? Yes. So if you want to convert something into something more valuable, you want to give energy into it, as opposed to fossil fuel. So we're in the carbon business. You take fossil fuel, oil, natural gas, high energy value, you go down and you make stuff. You make power, you make plastics, you make everything. If you start at the bottom, carbon dioxide, really stable. In order to get carbon dioxide or water up the chain, you got to give it energy. And so you need cheap energy in order to go uphill, in order to take advantage of the fact that you're going downhill the other way. And so the great thing about this is, with really cheap electricity, you begin to think about going uphill. That's the only takeaway message. In terms of splitting water, if it costs 4 or 5 cents a kilowatt hour, it's impossible. The amount of energy costs more than the hydrogen you want to make. At 1.5 cents a kilowatt hour, it's less than half the energy. Good deal. So then you begin to think of electrochemistry only because electricity is becoming cheap. You may not know, but let me remind you that virtually all chemicals in the world are made by thermochemistry, not electricity. Chlorine's made by electricity, aluminum's made by electricity, that's it. It's all thermochemistry, because electricity was too expensive. So when electricity becomes cheap, there's hope. All right, so what's the deal? What is the dream? You take carbon dioxide and water, you pour in energy in various mechanisms, thermochemical, electrochemical, we don't really care. You make hydrogen, you make CO, you make oxygen. And in the end, you want to make liquid. Remember the bar-tailed godwit and automobiles and airplanes, especially airplanes. You need liquid hydrocarbons. So how much does it cost to ship oil and store crude oil and halfway around the world and store it? And the answer is, you amortize that over the cost of the transportation and storage, is 2 cents a gallon of gasoline. Slow tankers are nearly free. So these super tankers are really an intercontinental transmission line. All right. I'm nearing the end, but I'm here to talk about climate change, but really writ large sustainability, water, agriculture, climate, energy. And in order to live a really sustainable world, the world population just can't increase forever. Okay. However, if you think about it, increased economic prosperity and global competitiveness, you ask any economist and any politician, they actually say we need more young people to have a smaller aging population. And they're so alarmed when the population in, let's say, the Midwest is declining because the economic competitiveness is growing smaller. How do you preserve the economic vitality? All right, so let me step back and say this is known as a Ponzi scheme. You have more people that you shall sell shares to, and it's okay. Okay, so let me tell you some good news. It turns out, and there is, in the red is India, in the green is Mexico, and in the yellow is Germany. And on the x-axis is national income, GDP per average person. And on the y-axis is the fertility rate. What does that mean? It means, on average, for every woman in that country, 2.1 is break even. You think 2 is break even, but there's mortality, so 2.1 turns out to be break even. And here's the amazing thing. India is not rich. Its mean GDP at this time, 2018, was $3,800 a year. And yet the fertility rate is very close to break even. Okay? We know in OECD countries, the United States and people like that, it's very negative. The United States is not quite negative because we have a large immigrant population. But the thing is going on is that we have a natural birth control. We can speculate as to what it was due to, but it's certainly due to women's education. It's certainly due to the lights are on at night. There's late night TV. There are other things to do. That seems to help. And of course, you know, when you get wealthy, you're thinking, oh my gosh, I have to pay my kids to go to college. And then even after college, they'll hang around. So whatever, I don't care. But it's happening in poor countries as well. So this is a natural thing. However, think about this. This is natural birth control. This is good, okay? So point number 1, how do you increase prosperity with declining populations? Japan is going to face this. Their replacement is like 1.2, really strongly negative. And so how do you have a declining population as you get older and you only have one kid and that kid is halfway around the world, and who's going to take care of me? And oh, by the way, who's going to help me get out of bed? Who's going to help me wash? All this other stuff. And so we have the means, maybe, human-assisted robots to help you get out of bed. It's like, you know, autonomous driving, that's not going to actually decrease the carbon footprint, but it means that as you get older, you will still have your mobility. Okay? So if you have human-assisted robots, they can help you take care of your parents because you don't have the physical strength to do this. This is a good thing. So we've got to figure this out. And we've got to start thinking about it. But the other thing is that we need a different measure of wealth. Because if you use just GDP, GDP is measured on how much you produce, which requires you consume it. 1 car per family is not enough. 2 cars per family is not enough. 1 car per adult, you begin to saturate, which happens to be the US norm of 1 car per adult if you include all the pickup trucks and everything. So the consumption of stuff is not going to be good because it gets you on this, continues the Ponzi scheme. I would say that a better definition of wealth would be quality of your health, especially in old age. education, including after K through 12 and maybe college. You actually have to continue education as the world turns and technology transfers. Stress level. You're worried about your kids. Are they going to be shot in school? Is my neighborhood safe? Connections to family and friends. So you need more than just GDP stuff to measure wealth. As long as you use wealth, everybody gears, and all the politicians will say, more stuff. And this is not tenable. So let me close by telling you something remarkable that happened in the last 20 plus years. This last year's Nobel Prize to physicists, 2 of them out of the 3, were for their discovery of so-called exoplanets, planets beyond our solar system. And the latest estimate from the serious literature is there may be in our own galaxy 10 billion Earth-like planets. Earth-like means there's liquid water, not too heavy gravity, so it's not oppressive atmosphere, not too light a gravity, so you won't have any atmosphere. Mars is too light a gravity. That's a lot, 10 billion planets. So this is great. That's our Milky Way. You know, we're here. This is taken with a wide-angle lens. And suppose, if you look at the probability, you maybe want to go 1/5 of the radius of the galaxy to find another Earth-like planet to colonize after we've trashed our planet. Okay? So let me remind you how you get out of the solar system. It's not by rocket fuel. You actually go by nearby planets, and the satellite goes in and whips around the planet, but because the planet is moving, it gives you a little boost. So you get boost, boost, boost. And by the time you get out there, you're going pretty fast. And in the graph on the right is actually the velocity of things like Voyager and these other things. And you see, as you go out of the gravitational pull of the Earth, it slows down. You whip by a planet, you get this little spike up, and it slows down. You get another spike up, and it slows down. If you really wanted to maximize the boost and not kind of look at the planets while you're going by, you can probably, instead of 20,000 kilometers a second, you can probably get up to 70 kilometers a second. That's really fast. 20,000 kilometers a second. Okay, how long does it take to get out of a galaxy? 45 million years. To get to 1/5 of the radius of the galaxy. 45 million years is a long time. Nothing we've made lasted 5,000 years, let alone 5. Okay, here's the other problem. You're now going 70,000 kilometers a second. You get to your planet, how do you land? Violently. Okay? So, let me close with one of my favorite pictures. It's taken on Christmas Eve, 1968. I was a college student. And it was called Earthrise. And after the last orbit around the moon, the capsule turned earthward. And the astronauts actually had handheld cameras to take these pictures. And the astronaut who took this picture, Bill Anders, said, "We came all this way to explore the moon. The most important thing is we've discovered the Earth." Think about it. Moon is not a good place to live. No air, no water, no magnetic field to shield you from cosmic rays, so you get a lethal dose of radiation. I hope I convinced you you ain't going somewhere else. And so this is a wonderful planet, but in the years since 1968, we've found that we've altered the destiny of the planet. It is largely caused by humans, and we have to take care of this one because there's really nowhere else to go. Thank you.